Let's see. So okay, I hope you can see my screen. I just wanted to check once, then we'll jump live. Let's see. So okay, I hope you can see my screen. I just wanted to check. Good morning, guys. Once, then we'll jump morning live. Let's begin. Okay. So yeah, let's start. Okay. So I'm hoping my screen. I'll just change the layout and all because I wanted to keep. Okay. Let's jump into take you forward and without wasting time. And let me exit from here. Disconnect. I think everything looking good. So yeah, right now we are solving the dynamic programming problem, and I will open QuickTime Player so that we can. Okay, it's already open. Yeah. So I think it's 50, right? So 75 using Python. By the way, so we are solving the. Let me close it and yeah. So LIS. So I haven't watched any tutorial yet. Let me reset it. So we were solving this problem. Okay. So what are the different options that I have followed so far? Longest increasing subsequence. Okay. Given an integer array nums return the length of longest strictly increasing subsequence. A subsequence is sequence derived from array by deleting some or no elements without changing the order of elements. Okay, that is subsequence. For example, 3627. Okay, 3 is subsequence of 3, 6. You are deleting 0, you are deleting 1, and you can delete either of 2, and then you are keeping 7. So the task is to find length of longest subsequence in which every element is greater than the previous one. Okay, so in longest increasing subsequence, I mean, yeah, all the elements should be greater than, like, it should be greater than the previous one. So it's like as all the elements should be sorted. I solved it using the recursion and memoization, where what I kept the last element. I kept one last variable, if you remember. So last time I solved it here. Last, I'm keeping index, keeping last so that we can track, and then I started from 0. So for 0 it will be -1. That means you don't have any last, and it is okay. It is working. So let me see the submissions, because it's been since few days I haven't solved any problem. So yeah, 4 July. So after 4 I haven't solved on 5th. That's 6th July. Okay. So now I wanted to memoize it. There are two options of memoization. There are actually 4 approaches. Binary search I will see it because I don't see how to solve it using tabulation. This is the approach that I was stuck, like on which I stuck. I was not able to get the exact solution for it, and then I thought okay, let me do it tomorrow. And tomorrow never comes, only today. Okay, so we have given numbers. Where are your numbers? Bhai, did you? Okay. 10, 9, 2, 5, 3, 7, 101, 18. Okay. This one was mine, this one was not. So first thing is like we have given a length of subsequence, you can say. Okay, so this is our example array. Now what I wanted to do, I want to find the longest increasing subsequence. So there are multiple options. So you will do, just we need to find a subsequence first. Subsequence. Okay. Subsequence means you are deleting some character from it. And then you are forming it. Okay, so what is the approach here? So in recursion, what I did, simply we are thinking like, okay, if I have to forget about the longest increasing subsequence, if you wanted to find the subsequence between two strings or arrays, what exactly we are doing? So we start, suppose you wanted to find the longest common subsequence between two, so it's extension of that, like longest increasing subsequence. So imagine you have two arrays given, array 1 and array 2 is also similar, and now you wanted to find out. So what you will do, you will start from one element, let's say n minus 1. You will start from this element. So here let's say 18, 101 and so on. So if we talk about this array, this is one, this is one. Now you'll compare. If both are matching, that means both are part of common subsequence. Common subsequence. Right. So you can add and then you can proceed. So now you wanted to check the another element, whether it can be part of it or not. So in the same way, okay, so there were options like, okay, if matching, then take that length. I mean this is 1 plus, and you will move to next element in the both. Otherwise you have another option, else you are not getting anything common, but you have two options, explore, only explore. So like you are keeping this and you are keeping like this, or you are keeping like this and you are keeping like this. So you are discarding from one element and then you are comparing. So it's like you are doing either I minus 1 or j minus 1, and you are keeping. So here if you are keeping, then I minus 1 j and j minus 1 I. So this is the option. Now what we are doing, now we need to find out it's not like longest. Oh man, what is this? Zoom in. Longest LIS, longest increasing subsequence. So you are given an array, and now I need to find out longest increasing subsequence. So what I'll do, imagine you are at a particular element and you want to decide whether it could be part of LIS or not. So what you'll do, you will look backward. Okay, if the last element that I took is smaller than this element or not. If it is smaller, then this could be part of it. Another options. So what are the different options for this element? You are at ith index. Now you have two options. Option 1, if last, just check the last index, okay? If last, so if array of last is less than, that means this one, previous element, whatever previous element that you considered is less than array of current, or you can say array of I. Okay, that means you can take it, right? Now it's up to you, take or not take. Okay, and reason behind why you maybe why not take can be also good decision, because suppose you are at 5 and now you are looking for, now you are just checking 6 8, and also then you got 7 8. Okay, imagine this is the location where you are, or this is the index where you are. So if you are taking it, then you will end up with, you will discard two elements, or your LIS will be 5 and 8. But imagine you are discarding this, then you have 7, you have 8, then your length will be 5 7 8. It will be higher than that. That's why you are exploring all the options that are available. So this is, and if it is not matching, that means it is bigger than this, so definitely you are what do I say, discard the last next number. For example, if the array is like something 5, and then you got 5, you got 4, then you got 7, you got 8. So if you are at 4, definitely it is smaller than the last element that you took. So you will say, okay, it's not possible, you cannot take it as a part of LIS, so you have only discard option. So not take, and you have to do solve it, and finally you have to compare this. These are the option 1, option 2, option 3, and you have to take max of op1, op2, op3, or you can say op1 and op2 is same as this one. Now we already solved it using regression and memoization. I'm just thinking how to solve it using table. So first thing, this represents I, index of the array element that we are processing. So we have array, right? So here different index or different elements will be there. So let's say 5, 8, 11, 15, 4. So 0, 1 and n minus 1. Okay, so these are nothing but the index of different elements. Or you can take, okay, I think we need to take till n, because if array of, otherwise we won't be able to get the base condition. So when index equals to n, so it represents index length, I mean not index, yeah, index only, so weird, I forget it. Okay, now second thing, so this is representing index. So you know what things we needed. First thing is index, second thing is last we needed. Last, whatever the value that we are getting from the last. And now think about last. What are the different values possible for the last? Okay. So different values that you can get for the last are, it could be -1 or -1, or it could be 0, 1, 2, 3 up to 2, n minus 1. Right. Last can go up to index, any index. It could be like n minus 1, that is the last index of it, or it could be you are starting from first. So minus 1 up to n minus 1. So I can say the length will be somewhere n length of this dimension. So I will start with 0, 1, 2, and we are going to, like for minus 1 we'll consider 0. Actually whatever index that you wanted to calculate, it will be minus 1 plus I or plus 1. So minus I plus 1, not I plus 1. Okay, so minus 1 represents 0, 1 represents 0, no, 0 represents 1, 1 represents 2. So it's like you are creating pseudo index, and n minus 1 represents n. Okay, now let's start filling. I mean, I'm not gonna fill, it's just like I am filling the base condition, and after that, so when index is n, imagine this is a condition where you traveled all the elements, or where you processed all the elements of array. You processed and you are here somewhere, you completed this one as well. Then what is the maximum LIS, maximum longest or longest increasing subsequence? What is the length of longest increasing subsequence? Definitely it will be 0. You won't get any elements that will be part of your LIS. So we will say 0, 0, 0. No matter what is the value of last, you will get 0. For all other conditions, what you will do? For all other conditions, it is like simply you are going to perform the same operation that you performing in the recursion. Yeah, you need to perform the same operations. So for example, you are at okay, ith index. So now you have two options. First thing is you need to check last. Okay, what is the value of last, and accordingly you will decide. So if array of last so first thing you have to decide two things here. If last equals to, so last, definitely whatever the value that you are going to get from it, like if you will traverse it, then you will get something that is not the real last value. So last will be you can say j minus 1. Okay, first thing. Then if last equals to minus 1, okay, that means you are starting from the first, or last, or you will say array of I will represent I minus 1, I only is greater than array of last. Okay, if this is a condition where the last element, either you are just starting this condition, or when you are comparing the current element, it is bigger than the last element that you choose, so definitely it could be part of LIS. Then what you will do, your result will be, for this particular thing, you will say current of I, and or you can say table of I and j will be something like 1 plus, now you are looking for the last. Okay, so now you got this one, and When you already covered it, then you will say, okay, table. First thing, the length was 1 minus, so I minus 1. Okay, oh okay, I'm confused now. Current element, when you are picking, you are at ith index. What exactly you are doing? So when you are picking an element, first you are deciding last, and when you pick the last, then you are saying, okay, no problem. What you are to do? 1 plus solve I plus 1. You are moving to next element, and just last will become current. Hmm. Last will become current. So I plus 1, last equals to current. So here I am starting from bottom. Is it right approach? Bottom up. Bottom up. What if I will start from 0? I equals to 0. That means you are in the first element. Then what I'll do? I equals to 1. You will take decisions. What was the last value? When you have 0 element, oh man, I stuck on the problem of what nums dot length 10 to the power of 5. Numbers can be negative. Okay. Okay. Let's do it. 0, 1, 2, 3, 4, 5, n. I mean, okay. So it is like index and it is like last. So here it will represent -1, 1, 0, 1, and so on. So if last equals to -1, index equals to n returns 0. So cannot, it's like it's not a bottom of dp. So your current decision will be required for next iteration, previous one. So you have to start from starting. So when index equals to 0, you have two options: take or not take. About OBS, what is time right now? 29 minutes wasted. Hmm, very bad. Confused. If you are at 0, how will you decide? In recursion base condition was something like if index equals to n, return 0. But when you are at index, index equals to 0. You are looking for the examples and you are exploring all the paths. So definitely you are completely relying on future results. And last matters most. Okay, intuition I'm not getting. Let me watch video. Hey, where is the video? Really? I don't have. In order to convert recursive code to tabulation, we try to convert the recursive code to tabulation, and here is the step. Declare array of n size n plus size. There are two changing parameter in the recursive solution: I, current index, and the previous index. Previous index, yeah, okay, last value. The maximum value of I can attain is n, where n is the size of array, and the value of previous line ranges from -1 to n minus, so we can split by plus, we can shift it by +1 to avoid. Okay, yeah, got it. Hence we need 2D array of size this. Okay, setting base condition case in array. In the recursive code, our base condition was I equals to 12, which means we exhausted all the elements and the LIS is 0. So in the tabulation approach, initialize the last row of dp, such as dp of n, and star as 0 represents that no elements are left to be considered. I was doing the same. Iterative computation using loop. Since the recursive call depends on I plus 1, depends on I plus 1. So we fill the table in bottom up manner, start iterating from I from n minus 1 down to 0. For each I iterate previous I minus 1 down to previous indicator. Last index you are taking or not taking. Okay, last index you are getting, and then oh god, I am not getting intuition. Okay, let me do it again. So this is nothing but 0 to n minus 1 n, because there are total n minus 1, minus 1 to n minus 1, there were range, and also here 0 to n. For n, when you exhausted all the elements, so it will be, result will be 0. Okay, for all others, you what you will do, there will be like I, there will be j. So last you will calculate, last will be j minus 1, because j is starting from 0. And now you will say, first thing, if how, when you will consider this element, options, consider or not consider. If last that means last equals to minus 1, or so array of I current index, current element you can say. Okay, so definitely you are checking the current element and you are looking for the last that you got. So if array of I is greater than the last, we are storing index, so array of last, then what we'll do, okay, you will say you have two options, take or not take. Take, that means you considered this element. Okay, then it will become like, okay, you considered this element, now table of I plus 1 next element, and current will be, okay, last will become current, so I will become last, else not take equals to table, you are moving to next element but you haven't took, so last will remain last only. Here last plus 1 you will keep it, because the way we are storing last. Okay, else part, so here you will take max of both, else that means you are not taking, because you don't have any option to other than this discarding this plus 1. Let's solve it. So I will use the optimized approach, then we'll jump into binary search, like we'll see if we can solve it. Okay, binary search, I solved the problem, so definitely I should be able to solve it. Let's see. So first we'll create next I will create an array and it will be of size n plus 1. So okay, I will keep 0 for underscore in range, and here let me give n as len of nums. Okay, and here we'll say n plus 1, so the total length will be n, I mean n plus 1 only length. Now previous I will keep the same because we are going to override it, no worries. Okay, now I in range, what you will do, you will start from n minus 1 and you will go till minus 1 and minus 1. You wanted to start from n minus 1 and you wanted to go up to 0, that's why I kept minus 1. Okay, for say in a range, and here you will say you are starting from 0 to n minus 1, so n, there are n plus 1. Okay, I mean now last will be your j minus 1 because you are using pseudo index. Okay, so you got this. Now if last equals to minus 1 or last equals to that means you can consider it. So take will be 1 plus, and then you will say next means I plus 1, and j will become like, here you are taking it, so I current element you will become last, not take. Okay, I just do not need to take it, and I will say take equals to 0, not take is nothing but here you are doing 0 you will get, and you are moving to next element, and I will remain j will remain same, so j will remain same. Okay, now this is You will say current. Oh, bro, what the fuck you did? Current of Z is nothing but max of take, not take. And finally, you'll say, okay, for each element, you are getting this. Return. Actually, you are starting from zero. So next of -1, that means 0. First index 0 and -1. Wow, so superb. 6 4. Current 0 and +1. Last equals to -1 on array of I. Array of last. Next of I. God. Previous indicator indication. J in range. So J is nothing but representing last element. You are deciding for current. So last element can be between I minus 1 and all the last elements. Okay, so 0 to minus 1 to I plus 1. Okay, I will do better. So it can go up to 0 to minus 1 to I, and every time you are doing 1. So I plus 1, you will say till I it could go, because you are taking minus 1 and 1 0, not I minus 1, I mean till I only. So this is index, last will be, so last index, it is representing last index. You see. What is this? God, somewhere I'm missing something. First thing, okay, I, this is okay. See, minus 1, and it can go up to I minus 1, because I is the current element that you are processing. Wait a minute. शोध नहीं हो रहा. Now I'm frustrated. What happened to internet? Oh wow, सुबह सुबह भी इसकी माँ की आँख स्ट्रेस बढ़ा रहा है मेरा. What happened to internet? Oh wow, सुबह सुबह भी इसकी माँ की आँख. कहाँ से इतने बाल निकल रहे हैं? I'm not observing it properly, I believe. So you are fall back into you are fall back to same square zero. Time consumed 54 minutes. Fuck. 9:44. I'm not able to visualize or reverse the recursion into memoization tabulation. It's very bad, yeah. So you are starting from last index and you started traversing. So you will say okay n minus 1 till 0, and you are doing okay. You are at traversing, like for example, if you are at n minus 1, then what will be the result? You will check. And your last can be between minus 1 to I minus 1. Right, for particular this element minus 1 to I, this is the possible options. J, that means okay, definitely index all the elements that you have processed so far. Wait a minute. If you are at I, so for I, what will be the last value? Last can be 0, 1, dot I minus 1, or you can say minus 1, 0 I. Okay, and reason is I minus 1 till, because for I you are calculating, that means before it anything can be potential I last value. So okay, you are taking this last became J, you are calling it as last. If J equals to minus 1 or array of that which column? Goodbye. Okay, so that means okay, let me think. So array of I, so either j minus 1, or if that is not the case, that means you are checking. Whatever the j value will be, Oh, what the heck? Oh, uh, can you hear me, guys? I don't know. If audio was audible, like you were able to hear me or not. I mean, I'm just confused about this problem because I'm not getting intuition. However, z equals to minus 1 area of I is greater than equals to area of j plus 1. So area of I is greater than area of I current element is greater than the last. So you will say last was z is representing minus 1 to 0 1 2. No, there is something wrong. Okay. Suppose z is not minus 1, z is 0. Zeroth element, okay. Oh, bro, I'm confused. Bro, z equals to minus 1 or area of I greater than equals to area of z. Z is 0, 1, 2, could be anything. Okay, now what are you doing? Take. You are taking it. Then next you are looking for I. Your last element will become I. Otherwise, okay, I means here it's 0. In the array it will represent I plus 1. Suppose you are taking last element as 0, I plus 1. Not take, you are not taking. So your element will remain same. So if it is minus 1, that will be z plus 1 next. प्रो कन्फ्यूज़न ही कन्फ्यूज़न है, सोल्यूशन का पता नहीं. Use your brain. Oh, wow. God, really? That means it won't work? Okay. Tutorial subsequence. Then what is the benefit of it? Oh, let me see. What is the time description of it? Okay, 10 to the power 5. Definitely it won't work. Oh, so I think the similar problem was this one I need to learn. Let me try from my end if I can do it. 15723. So if we talk about it, this is our element, right? Our goal is just find increasing subsequence. So why don't I do? It's like, let's say, what are the possible lengths? Length can go between 0 to n minus 1. I mean n. So length can be between 0 to n. No, no. Hmm. 7. If suppose you are at 7, and what you will say? What is the maximum longest increasing subsequence? No, bro. First, let me try it. 157. When is 157? And another one will be 1523. No, 123. Yeah, these are only two. Maximum possible length is 3. 15723. This is an array. Now we want to check. I know one option is like where you will take this element and you will start iterating through all the elements. You will say, okay, can 5 be part of it? Can 7 be for part of it? Is it okay to say like this? No. Brute force approach. Considering 1, then you'll say 5. You'll check 5. 5 is bigger than this. Yeah, you'll say okay. 5. Then you'll check 7. 7 is bigger than 5. You'll say okay. Then 2, not 3, not. You have considered 1 in the sequence. But there is also problem. 1 is 157. Another is possible 1, 2, 3. So you win. There are a lot of binary search. One five seven two three. Nothing is sorted. So if it is not sorted, then how can I solve it using binary search? What are the possible lengths? 0 to n. Let's imagine I want to form mid. Let's say m. So can I check like whether m length is possible or not? If possible, then how will you navigate to next m plus 1? I'm not getting intuition, bro.
So today we will be solving the problem longest increasing subsequence using binary search. In the previous two videos, we have solved using recursion, memoization, space optimization, tabulation.
Where is the videos? Where are the videos? I mean,
In this video, we will be discussing the tabulation approach via the memoization, and then we will be moving across to discuss the rather big of an approach that you'll find in all the blocks and everything. Okay, so going back to the recursive code. Okay, going back to the recursive code. How do you convert this portion of recursive code into a tabulated code? That's a very big question. Now, if you have been following this TPC. So today we will be solving the problem longest increasing subsequence using binary search. In the previous two videos, we have solved using recursion, memoization, space optimization, tabulation, and an algorithmic approach. These approach has been covered in the previous couple of videos, but we did see that the constraint was n equal to 10 to the power 5, and the best we could do was time complexity of big O of n squared and the space complexity of big O of n. This was the best that we had done till now. But if n is 10 to the power 5, n square is 10 to the power 5 square is 10 to the power 10 operations, which is definitely giving you RTLE. So we definitely cannot do this, right? So that's where something like binary search comes in. Can we find LIS using binary search? Now you'll find a lot of videos where the intuition is missing. Like I went through a lot of videos, but the intuition was missing. So in this video, my main focus will be to give you the thought process. Because once you get the thought process, the algorithm is very, very simple. So prerequisites are you should be doing binary search, and there is a lower bound and there's an upper bound video in my channel. I'll be putting the link in the description. Go back and watch it, and after that, come back and watch this video. Okay. If you don't know about it, well and good. So let's get started. First of all, what is LIS? You know, is longest increasing subsequence. Like you can call a subsequence like 1, 8, 4, 6. This is a subsequence, not increasing. You can call something like 1, 8, 9 as an increasing subsequence. Increasing. Okay. Similarly, you can call something like 1, 4, 5, 6, 9 as the longest increasing subsequence of length 5. Subsequence, you know, a contiguous or a non-contiguous one, but it should follow the order. Like you can't be like 1, 8, 7, 6. This is not subsequence because 8 is before 7, but actually 7 is before 8. This is not a subsequence. Okay, so we saw that the longest increasing subsequence over here was 1, 4, 5, 6, and 9. Okay, so how do you actually solve this particular problem? That's a big problem. So how do you approach this problem? So what I will say is, okay, let's try to go across every element and try to form subsequences. That's my thinking. So I'm like, okay, initially when I'm at 1, okay, let's form a subsequence with 1. Makes sense. Next, let's go to 7. Do I need to form a new subsequence with 7, or can I just attach it over here? The answer to that is, let's attach it over here. Why? Because if you form a new, it will be of length 1. But if I attach it, it is still increasing. And it is having a length 2. Okay. Let's move to 8. Now if you're having 8, can you attach it over here, or will you prefer this? You can, because 8 is still greater than 7. Perfect. It is still greater than 7. So I've attached it. Next I go to 4. So I see there is 4. But if I attach it over here, it will not be increasing, because 8 is greater than 4. It will not be increasing. So I can either start with 4, but my brain says, but try one. There is one which you can take and you can attach with 4. So I'm like, okay. Makes sense. Next, I go to 5. The moment I go to 5, can I attach it here? The answer to that is no, straight away. You cannot. Can I attach it over here? Yes, straight away. You can. Next, I go to 6. I have a 6. Can I attach it over here? No. Can I attach it over here? Yes. Perfect. Next, I go to -1. Where can I attach it? Now, my brain says we can't attach it. We cannot attach a -1 here. We cannot attach a -1 here. But we can start fresh. Will -1 have anything before? No. It's the smallest. So I will have -1 right before this. Perfect. Next, I go to 9. So when I go to 9, I can attach 9 here. I can attach 9 here. I can attach 9 here. So assuming I attach to everyone, assuming it's over. So once you end it, you see this is a length 4. You see this is a length 5. You see this is a length 2. And eventually, the length 5 is the longest one, and that is the length of the LIS. But will you actually go across and generate all these subsequences? Because it's going to be very heavy. It's going to be taking a lot of time, because if you make new subsequences at every junction, it's going to take up a lot of space. Because if you're aiming to make a new subsequence at every step, it's going to take up a lot of space. So we will definitely not move this way. But this is an intuition which helps us to think of binary search. So tell me one thing. Like I don't need to print N6. I just need 5. So can I do something like this? When I was carrying 178 and this was done, when 4 came in, can I say 178? Let's rewrite 4 over here. Can I do something like this? Rewrite the same subsequence. Can I do something like this? And the answer to that is yes, right. We can do it. And let me show you what I'm actually talking about. Because we're just concerned about the length. We are at 1. Let's have 1. We are at 7. Let's have 7. We are at 8. Let's have 8. We are at 4. Instead of making 1 4, since we are actually not concerned about the LIS and we're concerned about the length, we will say, where can 4 fit in the existing subsequence? I say 4 can fit in here. So what you do is, remember, you take the 7 out, and you say 4 can fit in here. Remember this, that it does not mean 148 is a subsequence. No. I'm just making sure instead of storing 1 4 separately, I stored 1 4 right over there to save space. Even if someone like 9 comes in, and because I know if 8 is there, why is 8 here? Because previously 7 was there. That's the reason 8 is here. That is something which we definitely know. So we are sure that before 8 there is something smaller, which is 7. Now we have overwritten it, but we are not concerned about the subsequence. That's why what I did is, instead of creating a new, I overwrote the 7. I overwrote the 7 to 4 because it's okay to overwrite, because we're not concerned about the LIS, we're concerned about the length. So I overwrote it at that place.
Internet. Crazy.
Oh, let's move across to the next, which is 5. Okay, where can 5 be? I either go and create like 1 4 5, or I either say let's not create, and instead of that, let's omit 8 and write 5, because either you're carrying 1 7 or either you're carrying 1 5. It still makes the same sense, right? Okay, let's go to 6. The moment I go to 6, I'm like, okay, fine. Where can I have 6? Right after this. Amazing. The moment I have -1, where can I have it? I can definitely have it right over here. Replace it. So I replace it over here, saying not 1, it's going to be -1. Where can I have 9? I say right after this. So this is not the subsequence. This is definitely not the subsequence, but this gives replace it. Where can I have it? Okay, fine. Let's go to 6. The moment I go to 6, I'm like, okay, fine. Where can I have 6? In 1 5. It's still 5 because and instead of that, let's omit 8 and write 5 because either you're carrying 1 7 or either you're carrying 1 5. It still makes the same sense, right? Okay, let's go to 6. The moment I go to 6, I'm like, okay, fine. Where can I have 6? Right after this. Amazing. The moment I have -1, where can I have it? I can definitely have it right over here. Replace it. So I replace it over here, saying not 1, it's going to be -1. Where can I have 9? I say right after this. So this is not the subsequence. This is definitely not the subsequence, but this gives you the length. The length of the final array will be your answer, which is 5. Because you replicate it by putting those values. You replicated the same space by putting those values. That's how you can easily do it. Now, why binary search? Okay, very straightforward if you, again, just omit this off. Yeah, this is omitting this. Why binary search? Again, a very simple one. Because initially you had 1, then you had 7, then you had 8. The moment you got 4, you want to insert 4. If there is a 4, you insert it at that place. Or you say, hey, listen, there is no 4. So please go across and insert it right after 4. Right at the first element after 4. At the first element after 4. Can you please do it for me? Right at the first element after 4. So since you know this is sorted, in order to insert 4 here, you can simply do a binary search. And binary search will say 4 will go here. Next you go to 5. Binary search will say first element after 5, that's 8. Binary search will say I'll go here. 6. First element after 6, no one, so goes here. First element after -1, that's this. First element after 9, that's this. That's how you get the length. That's how you replicate. That's the thought process, simple thought process behind the binary search solution. So in C++, there exists a function like lower bound. Like you might argue, okay, let me just give you one more example. If array is given something like 1, 4, 5, then a 4, then a 2, then an 8. So what will happen in this case? Because you see repeated elements. So initially you had 1, so you don't have anything, so you put it across. Okay. Next you have a 4. Next you have a 4. So you again right after 4. So that's very good. Next you have a 5. You put it. But when you look for 4 again, if there exists a 4, you just rewrite it over there. Because that's what you do. You don't put it across anywhere else. Next you give a 2, so this is where it goes. Next you get 8, this is where it goes. So this is the length. Length is going to be 4. Again, is it practical enough? Yes, because 1, 4, 5, 8 can be the subsequence. Can you regenerate the subsequence by binary search? The answer is no. Then you have to store a lot more things. But you can easily get the length by accessing the length because you optimize space. Instead of carrying different subsequences, you reuse that space and you created it. So it's time to actually now go back and code it. So in order to remember this, our main intention of binary search is if there is an element as array of I, find array of I. Like in this case, if you see, when I inserted 4, I inserted at the place of 4. I inserted at the place of 4, right? So either find the array of I, and if this is not found, find first greater, the first element that's greater than array of I. That's it. And in C++, this can easily be done using a function lower bound. The lower bound, if you're doing a lower bound on any array, it gives you the first index, it gives you the index of array of I if exists, or gives you the first index which is greater than array of I. In order to understand it in depth, you can watch the video link in the description. Okay, so guys, it's time to check out the code now. So in the iPad, if you see,
at starting, our array will be having something like 1 only. Then what we'll do? 1. Then we'll add 5. 5 is bigger than the last index. You will say okay. So we will add 5. Now you will be having 7. Seven is bigger than the last index, so definitely you will say okay. Now 2. So 2 you will say okay. 2 is not bigger than this. Then you will find the lower bound. So you will check okay, is 2 available in this one? If so, then replace with it, or the first element that is greater than 2. So definitely it will be 5. So your array will become 1, 2, 7. Okay, now you will get 3. So 3 you will say okay, find the 3 or first index greater than or first element greater than 3. So you will say no, 2 is not there, 1 is not, 2 is not, and then you will say 7 will be, so your length will become 1, 2, 3. And I want to test out with other examples. Ten 9 2 5 3 7 101 18 2 5 3 7 1 1. Okay, so 10 9 2 5 3 7 1 1 18. So these are the numbers. So at starting our array will be 10 only. We'll be having 10. Okay, 1 minute bro. We'll be having 10 10 9. You'll say okay 9. So okay, now 9 is not greater than this. So you will say okay, let me find the either 9 or greater than the 9 first element that is greater than 9. So you will say 10. So it will become 9 only. Then 2. So you will say it will become 2. Then 5. 5 is greater than 2. So you will say 5. Then 3. 3 you will say okay 3. It's like a here you will say find it greater than. So you will say 2 and 3. Now 7. 7 is greater than this. Okay. 101. 101 is greater than this. Then 18. 18 you will say okay it's not bigger than this but I can fit it into somewhere. So you will say okay 2 3 7 101. So say it's bigger than 7. So you will say 101. Let's see if it's the index. So you will say it will become 18 and the length will be 4. But how to get it? I mean, yeah, literally, I'm feeling like okay, this is the intuition that you got because you watched video, bro. Pretty hectic. Okay, let's do it. First, let's do it. So, what I'll do, I will start iterating I in EL or range, and we will create one array. And we'll keep on appending the element. So lower bound in a sorted array. Array start int and element. So this is the lower bound condition. So what we'll do, array of mid is less than the element that we are looking for. That means move forward. Array of mid is greater than oh no, else if array of mid is greater than the element, that means it could be result, right? Result can be mid, and you will try to find the closer result or the closer element to the matching the target element. So you will say result can be mid. Okay, now what I'll do, you will say int will be mid minus 1. Okay, else that means you won't get the result. The current element is smaller than this. So start will be mid plus 1. Okay, wow, wonderful, bro. Start equals to, let me define first lower bound. This array I'm giving simply self dot, because it's Python, right? Array, and then simply giving element. Start I'm calculating 0. End will be nothing but len of array, and you will say while start less than equals to end, result will be minus 1, he will say. First element that is bigger than this or equals to this. Can it be minus 1? No. Can it be 0? Yeah, if all the elements are bigger than it. And what else? And what is other condition? It could be, it could go up to n. N means last element, or last plus 1. That means you need to append it at the end. If so, I'll say mid equals to start plus end by 2. If mid, area of mid equals to el return mid, else area of mid is greater than equals to greater than el. What does it mean? Bigger than this, area of mid is bigger than the element that you are looking for. So result could be el, and what you will do, you will try to reduce the number. So mid or end Okay, so this is one thing. Now for each element, you have array will be something like this. For I, if el if el okay, if len of array equals to 0, or el last element to the current element is greater than what, the array of -1. These are two conditions. So you will say, okay, array dot append, simply you are appending the element. Else, first find lower bound. LB is lower bound, self dot lower bound, and you'll say, okay, this array I'm looking for el, and once you got lower bound, so we'll say array of LB is equals to el. Okay, these are the two conditions. Finally, return len of array. How is that possible? Bro, I'm always making mistakes. Array element is not printing anything, just Bancho array blank for real in nums if len of array equals to 0, or el current element is greater than array of -1. Array dot append el, else lb lower bound self array element. So let me print lb first. Let me check. Okay, -1. Still, it's somewhere it's issue. Okay, let me do one thing. LB and array. Starting array is 10, Starting 9. Nine. So the main culprit is here. 9. How can I get 9? Equals to 0. End equals to len of array minus 1. Result equals to minus 1. While start less than equals to end. Pass clock. I was planning to do a lot of things. 0 0. Oh, okay. Problem is result I kept mid. Instead of mid I kept mid. Oh god, definitely I need to visit it again. Solve it again. You will forget it. Forget the approach. Now let me jump to that problem where subsequence. What was the lead code problem? Contest. Daily chicken, what I'll do? Come back later. Okay. Weekly contest. People are doing like hell. My brain is like subsequence after one replacement. Subsequence. A to D. What is A to D? Bro, are you speaking or what?
Hello, hello, hello.
Yeah, bro. Hello.
Um, And yeah, that's all I guess.
Hey, bro.
This was the easiest problem by far. And yeah, it was actually good one. It required some critical thinking and some amount of thinking. So here you are given an integer elements, okay? Sum of all integers. The max digit range here is 5. Yeah, how can you like uh, the time complexity would be at size of string is for both the string for S and T, it would be less than equal to 10 raised to 5 greater than equal to 1. This was actually a good problem. Yeah, this is just implementation exactly. This was easy problem. Let's move to second question, I guess. I think today's PCD would be a short one, right? Because for this we don't require that much implementation. But yeah, let's go. This is the second problem. Subsequence after one replacement. You are given two strings S and T consisting of lowercase English letters. You may choose at most one index in S and replace the character at that index with any lowercase English letter. Return true if it's possible to make S a subsequence of T. Otherwise, return false. Cool. Let's see it. Problem number B. This was actually a good problem. For folks who are best transmitted from good forces of move from unfit transmitted from the problem. For folks who are best transmitted from good forces of move from another platform like code forces or code shift, like they would have trouble solving this, right? Because it requires algorithm. We will see it. Let's see. So basically, we are given two strings, S and T. These are strings. And second, we have one operation, only one. And this operation, we can change any letter of T, right? And we can basically replace it, change or we can replace it with any alphabet. With any alphabet. Cool. Third, we have to find if S is a subsequence of T. 3 points, only that also the size of string is for both the string, for S
10 to
and
power
T,
5.
it would be less than equal to 10 raised to power 5 greater than equal to 1. Cool. This is the problem, right? Let's see some example. Let's see the example which we are already given. Cat and chat. Right.
Hmm.
I hope everyone is aware of subsequence. Subsequence means uh, all the subsets where we can choose some characters and when we extract them in order. We maintain the order and we can pick any character. Like we don't have to basically The character should not be continuous or some other condition. We can pick any character. For example, CT is a substring, CA is a substring, CHA is substring, dot. Cool. I have to find if this cat is also a substring perfect. You can actually see it, right? CAT. Our T is equal to CHAT. If I take this character, this becomes cat. Yeah, it's a substring, yes. You just have to print true or false here, right? Because it's not code process. Yeah, it's true. But what if, let's take a more example. S is equal to KAT and T is equal to CHAT. Now, does the subsequence exist? Is this subsequence exist? The answer is false. You can see it, right? Mere observation tells us that there is no K here. Okay, what can I do? Now, what can I do? I have this operation that I can change one character. Change one character. Okay, so I'll change. What character can I change? CHAT. What character can I change? Let's change this. I can change this to K. So this becomes KHAT. Hard actually, but yeah. This is now S is a subsequence of T. This is cool. You did that. But like, okay, cool. This is the second example that we have to change this right now. The problem arises is first we'll check if S is subsequence. How can we check it? We can easily do 2 pointers here, right? 2 pointers. There, one pointer would be at S and one pointer would be at T. And we'll simply start. We'll start with the first element of both. We'll check, if this matches, we'll increase their pointers. So SI, let's say TI is its pointer, we'll increment it and SI will increment it. If they both are not equal, we'll just move forward in T. We'll move forward in the string T itself. Because S, we have to ensure that S exists at T. Right. So this 2 pointer approach, I hope this is good to go. I'll show you some example because someone told me the solution in here. So yeah, let's say this is our T and our S is equal to C. We'll start the very first pointer from here and here. Both are equal, then we'll move the pointer. Both sides. Here and here. Both are equal? No, they are not equal. So we'll move the pointer only at T. Because finally we need the T to include S, right? So now we will here. Both are equal? Yes. Now we'll move the pointer. If the pointer reaches here, like it's already traversed that higher, we'll just return to it. Right. Okay, cool. This is the first step, right? If it's already a subsequence. But even the step, later we will include all the steps in one. Now second. This is actually the 2 pointer approach is very important to know. The second thing is, what if not? What if not? For example, S equal to cat and T equal to CHAT. Now we have to do it, right? Now how will this 2 pointer approach will go? CHAT and this is equal to T, S equal to CHAT. Right. We will be here, they don't match, so we'll move the pointer, they don't match, we'll move the pointer, don't match, we move the pointer, they don't match. Now, how will we know that what character to replace? There might be 2 approaches. There might be greedy, or there might be some other approach. Right. Some other is usually DP or recursion, or sometimes you just apply dynamic programming into recursion. Take this framework for example, just always helps. So if it can be solved by greedy, then it's cool. Otherwise, if it cannot be solved by greedy, then we have to do some sort of dynamic programming or like some sort of recursion where we have to basically test all possibilities. Right. So greedy, I think it's problematic. We never know which we can change, right? Because let's say we change this C, right? As is the first letter, for this case it might be good, but there are plenty of cases that will fail, right? For example, let's say we have HTAP, right? And we have to basically basically find, let's say, T80, sorry, A double T, right? So what will happen? Here, this is T and this is S. They don't match, move the pointer. They don't match, move the pointer. Oh, they both match, move pointer on both. They both match, okay, cool. Now this T is remaining, right? Where can we place this T? We know that we already have used the suffix, right? Now the thing is, if we are using greedy, what's the problem statement here? E, we cannot add T. Right, match, let's say T80, sorry, A double T, right? So what will happen? Here, this is T and this is S. They don't match, move the pointer. They don't match, move the pointer. Oh, they both match, move pointer on both. They both match, okay, two match, move the pointer. Oh, they both match, move point. They don't match, move the pointer. They don't match, move the pointer. Oh, they both match, move pointer on both. They both match, okay, cool. Now this T is remaining, right? Where can we place this T? We know that we already have used the suffix, right? Now the thing is, if we are using greedy, what's the problem statement here? E, we cannot add T, right? We can't add T, right? The problem statement here is, where should we add T? But that's the wrong problem statement. You can add T anywhere, but it would not result in answer. Either if we change this X to A, then only we can get the answer, right? There are no possible cases, right? So basically, greedy would not work here because there are plenty of cases and we never know where we could end it, right? Then what are we remained with? AP or recursive? Cool. How can we solve it with BP or recursive? So this is T, right? S is equal to, yeah. How can we solve it with BP? There is one thing. Again, the two-pointer approach is very important, right? We are going to build on it, right? We know we have the two-pointer approach, right? We can keep two variables, right? The first two pointers actually for S. One is SI, one is, for example, let it be SSI. What does this tell? This tell pointer, then we have not used any operation, and this pointer when we have used one operation or all operation because we only have one operation, right? Make these two pointers for us, and for T we will have one pointer Ti. Why this is important? Because this helps us include all the possible cases. How? Notice something. The concern is not that what letter or what position we have to choose. This is very important. Concern is not that what character we have to change. What character we have to change. Or with which character. We don't have to think about that. We just have to tell if this subsequence fits in this or if S is subsequence of T. What are you trying to say? Let's say we have chat CHAT and KAT. Now this is T and this is S. Initially our S we will have SI, right? The pointer where we have not used any operation. SSI we have used the operation in PL. Right, this we are going to basically iterate in a for loop. Now, initially we are here and here. SI will initially be 0. We are taking 0 based indexing, all will be 0. Cool. First we will check, is C equal to K? No. What we do, we increment the T. Right. So the T here would become 1. Right, so we incremented the T here. Cool. What about SI? SI would remain same here. But what about SSI? Do we have any operations here? We have not taken any operation. Let's say we did an operation here. Let's assume we did it here. Then what would be this pointer would become 1. Why? Because we assume we made the operation here. If we made the operation here, we change C to K, or to match it. If they both are equal, then both pointer move, right? So this is exactly what we do. So SSI becomes one. Now SSI is here. SSI, SI is here, and TI is here. Now again we check. Is H equal to SI? No, it's not. Both are not equal. Then S will remain the same here. It would be 0 after this matrix has been. Is H equal to A? Not. Then that means this one could remain same. Otherwise, what we could do here is make this, if this SI is equal to 0, right? We can do an operation here again. What if we did an operation here? What if we did operation for SI? We can change this H to K. If we change this to K, then these two becomes equal. Then the answer here could be max of this one we already had, SSI. Otherwise, SI plus 1. Can I say this? Why? Because this SI was here, right? I assumed what if I did right? Again, the max would be SI plus 1 is again 1 here. So this would be 1. We move forward. SSI, cool. This we will increment it. We have not applied an operation. So this plus 1, because we can always apply first. Implemented the operation, then we just have to check. For example, here, when we were here, we just have to check. Oh, they are equal to. If they are not equal, for example, H and A, they are not equal, we cannot implement SSI. But if they are equal, we can implement SSI as well. Also, we can check if the SI is the index when we have not applied an operation. So this plus 1, because we can always apply operation with this index, right? And this SI does not come from here, it comes from here. SI plus 1. Cool. These are the DP state that we have to manage. And in my, like you can see, we can only keep the pointers as well, right? Pointers are sufficient. Pointers are sufficient. We don't have to keep the entire vector, the vector DP. It could be 2D DP, right? At last 2. Where 0 tells we have not applied any operation, we have, and I1 tells we have applied any operation. Right? 1 here. Right? And then we can choose the transition state. This you can map with SI, and this you can map with SSI. These were done to make it more clear and break it down from first principle. Entire flow actually. Right? Again, the max both are not equal. Then this is very important. Concern is not that what character we have to change. What character we have to change. We don't have to think about that. We just have to tell if this subsequence fits in this, or if S is subsequence of T. What I intend to say, let's say we have chat C H A T and K A T. Now this is T and this is S. Initially our S, we will have SI, right, the pointer where we have not used any operation. SSI, we have used the operation in TI. Right, this we are going to basically iterate in a for loop. Now, initially we are here and here. SI will initially be 0. We are taking 0 based indexing, all will be 0. Cool. First we will check, is C equal to K? No. What we do, we increment the T. Right. So the T here would become 1. Right. So we incremented the T here. Cool. What about SI? SI would remain same here. But what about SSI? Do we have any operations here? We have not taken any operation. Let's say we did an operation here. Let's assume we did it here. Then what would be this pointer would become 1. Why? Because we assume we made the operation here. If we made the operation here, we change C to K, to match it. If they both are equal, then both pointer moved, right? So this is exactly what we do. So SSI becomes 1. Now SSI is here. SSI, SI is here, and TI is here. Now again we check. Is H equal to SI? No, it's not. So both are not equal. Then X will remain the same here. It would be 0 after this syntax has been. Is H equal to A not, then that means this one could remain same. Otherwise, what we could do here is make this, if this SI is equal to 0, right? We can do an operation here again. What if we did an operation here? What if we did operation for SI? We can change this H to K. If we change this to K, then this becomes, these two becomes equal. Then the answer here could be max of this one we already had SSI. Otherwise, SI plus 1. When I say this, why? Because this SI was here, right? I assumed what if I did operation now? If I did operation now, then SI would become SI plus 1. Cool. And this SI plus 1 would go in SSI because now we have used our operation, right? And this will obviously increment. This is the entire flow actually, right? Again, the max would be SI plus 1 is again 1 here. So this would be 1. We move forward. SI again remains 0. Now we are here at A. TI is here. And SI now is again here and SSI again here. SSI is equal to 1 here. Again. Cool. Now here is A. Is A equal to SI? No. Again it would be 0. Is this A equal to SSI? Cool. Then we will increment it. So this becomes 2. Cool. Now again, what if we did operation here to make it equal to SI? Then it would be 1 plus SI. Max again. Max here is 2, so we will take 2, and this we are just going to increment. Now the last step, is this T equal to K? No, again 0. Is this T? Now here is our SSI, right? We have jumped from here to here. Is this T equal? Okay, cool. This will be 3. Now what? Again, we can actually make this K and this SI will increment, so this will become 1 plus SI, right? And here this incrementing, as this is max, this is 3. Now what we have to check, if max of SI or SSI is greater than equal to S dot size. What is S dot size? Here is equal to 3 and the max of this is also equal to 3, then yeah, it's true, we are going to return the answer. I hope this is a simple DP, right? You just have to take 2 transitions in every state. In every state, first, if we have already implemented the operation, then we just have to check. For example, here, when we were here, we just have to check, oh, they are equal to. Sequence was that higher, then just return. Actually, C8, right? C-A-T. Our T is equal to C-H-A-T. If I take this character, this and this becomes cat. Yeah, it's a substring, yes. We just have to print true or false here, right? Because it's not code process. Yeah, it's true. But what if? Let's take one more example. S is equal to KAT and T is equal to CHAP. Now, does the subsequence exist? Is this subsequence exist? The answer is false. You can see it, right? Your observation tells us that there is an okay here. Okay, what can I do? Now, what can I do? I have this operation that I can change one character. This cool that we have checked. How can we check it? We can easily do two pointers here, right? And with will increase their they will increment it. If they both are not equal, we'll just move forward to ensure that as good to go. I'll show you some example because someone told me to say a solution in here. So yeah, let's say this is from here and here. Both are equal, then we'll move the pointer. Both sides. Here and here. Both are equal? No, they are not equal. So we'll move the pointer only at t. Because finally we need the t to include s, right? So now we are here. Both are equal? Yes. Now we'll move the pointer. If the pointer reaches here, the pointer reaches here, like it's already traversed that entire, we'll just return to it. Right? Okay, cool. This is the first step, right? If it's already a subsequence. Now second, yes. For example, s equal to cat cat and t equal to chat. Now we have to do it, right? Now, how will this two pointer approach will go? Chat and
Two pointer
is equal
approach.
to t, s equal to cat. Right? We will be here. If we will be here, they don't match. So we'll move the pointer. They don't match. We'll move the pointer. Don't match. We move the pointer. They don't match. Good. Now, how will we know that what character to influence? There might be two approaches. There might be greedy, or there might be some other approach. Right? Some other is usually DP or recursion, or sometimes you just apply dynamic programming to recursion. Take this framework for example. Just always right. So if it can be solved by greedy, then it's cool. Otherwise, if it cannot be solved by greedy, then we have to do some sort of dynamic programming or like some sort of recursion where we have to basically test all possibilities. Right. So greedy, I think it's problematic. We never know which we can change, right? Because let's say we change this C, right? As is the first letter for this case, it might be good, but there are plenty of cases that will fail, right?
Not
For
right, bro.
example, let's say we have HEAP.
Are a class of algorithm that make locally optimal choice at each step with hope of finding global optimum solution. Okay.
Right, and we have to basically find, let's say, CAT, sorry, A double T, right? So what will happen? Here, this is T and this is S. They don't match, move the pointer. They don't match, move the pointer. Oh, they both match, move pointer on both. They both match, okay, cool. Now this T is remaining, right? Where can we place this T? We know that we already have used the suffix, right? Now the thing is, if we are using greedy, what's the problem statement here? E, we cannot add T, right? We can't add T, right? The problem statement here is, where should we add T? But that's a wrong problem statement. You can add T anywhere, but it would not result in answer. Either if we change this X to A, then only we can get the answer, right? There are no possible cases, right? So basically, greedy would not work here because there are plenty of cases and we never know where we could add, right? Then what are we remained with? AP or recursion? Cool. How can we solve it with BP or recursion? So this is T, right? S is equal to cat.
cut,
How can we solve it with T?
Kit Kat.
There is one thing. Again, the two-pointer approach is very important, right? We are going to build on it, right? We know we have the two-pointer approach, right? We can keep two variables, right? The first two pointers actually for S. One is Si. One is, for example, let it be SSI. What does this tell? This tell pointer then we have not used any operation, and this pointer when we have used of one operation or all operation because we only have one operation, right? Make these two pointers for us, and for T we will have one pointer Ti. Why this is important? Because this helps us include all the possible cases. How? How? Notice something. The concern is not that what letter or what position we have. This is very important. Concern is not that what character we have to change. What character we have to change. Or with which character. We don't have to think about that. We just have to tell if this subsequence fits in this or if S is subsequence of T. What I intend to say, let's say we have cat CHAT and KAT. Now this is T and this is S. Initially our S we will have SI, right? The pointer where we have not used any operation. SSI we have used the operation in TI. Right, this we are going to basically iterate in a for loop. Now, initially we are here and here. SI will initially be 0. We are taking 0 based indexing, all will be 0. Cool. First we will check, is C equal to K? No. What we do, we increment the T. Right. So the T here would become 1. Right, so we incremented the T here. Cool. What about SI? SI would remain same here. But what about SSI? Do we have any operations here? We have not taken any operation. Let's say we did an operation here. Let's assume we did it here. Then what would be this pointer would become 1. Why? Because we assume we made the operation here. If we made the operation here, we change C to K, to match it. If they both are equal, then both pointer move, right? So this is exactly what we do. So SSI becomes 1. Now SSI is here. SI is here and TI is here. Now again we check. Is H equal to SI? No, it's not. Both are not equal. Then S will remain same here. It would be 0 after this index has been. Is H equal to A? Not. Then that means this one could remain same. Otherwise, what we could do here is make this, if this SI is equal to 0, right? We can do an operation here again. What if we did an operation here? What if we did operation for SI? We can change this H to K. If we change this to K, then these two becomes equal. Then the answer here could be
H to K. Okay.
max of this one we already had SSI, otherwise SI plus 1. Okay.
SSI
And I say this, why? Because this SI was here, right? I assumed what if I did operation now? If I did operation now, then SI would become SI plus 1, 2. And this SI plus 1 would go in SSI because now we have used our operation, right? And this will obviously increment. This is the entire flow actually, right? Again, the max would be SI plus 1 is again 1 here. So this would be 1. We move forward. SI again remains 0. Now we are here at A. TI is here. And SI now is again here and SSI again here. SSI is equal to 1 here again. Cool. Now here is A. Is A equal to SI? No. Again it would be 0. Is this A equal to SSI? Cool. We will increment it. So this becomes 2. Cool. Now again, what if we did operation here to make it equal to SI? Then it would be 1 plus SI. Max again. Max here is 2, so we will take 2. And thus we have this. Just to increment. Now the last step is this key.
it's 2 if you are up changing.
Equal to K? No. Again 0. Is this T? Now here is our SSI. Right? We have jumped from here to here. Is this T equal? Okay, cool. This will be 3. Now what? Again, we can actually make this K and this SI will increment. This will become 1 plus SI. Right? And here this incrementing as this is max, this is 3. Now what we have to check, if max of SI or SSI is greater than equal to S dot psi. What is S dot size? Here is equal to 3 and the max of this is also equal to 3. Then yeah, it's true, we are going to return the answer.
Okay, that means you have finished all the elements.
I hope this is a simple DP, right? You just have to take 2 transitions in every state. In every state, first, if we have already implemented the operation, then we just have to check. For example, here, when we were here, we just have to check, oh, they are equal to. If they are not equal, for example, H and A, they are not equal, we cannot implement SSI. But if they are equal, we can implement SSI as well. Also, we can check if the SI is the index when we have not applied an operation. So this plus 1, because we can always apply operation with this index, right? And this SI does not come from here, it comes from here. SI plus 1. Cool. These are the DP state that we have to manage. And in my, like you can see, we can only keep the pointers as well, right? Pointers are sufficient. Pointers are sufficient. You don't have to keep the entire vector, the vector DP. It would be 2D DP, right? And dash 2. Where 0 tells we have not applied any operation, we have, and I1 tells we have applied any operation. Right? Done here. Right? And then we can choose the transition state. This you can map with SI and this you can map with SSI. These were done to make it more clear and break it down from first principle.
What the heck? Zero one presents as I. This is I.
Full chat fly, so I
Okay.
A and SSI equal to B. Okay, S index and then special S index. Now just you can map it out. Right? We have
If B less than size, S dot size. Okay, then what are the options? S of A equals to T of I means these two are matching. So you will say A plus plus, and now you will take max. What? Okay, that means you are not basically you are doing one operation.
the size is less. Otherwise, we have already covered the entire array, right?
Where is the DP fucking A?
Condition has not already matched. You can, if else, you can actually return go through anyways because that means we have already traversed the entire array. Right? Just map it with it, and you will know if A equal to A or B, and even size is equal to S dot size. That means we have passed the entire array true. Otherwise, false. Right? Again, if the element matches B, we did it with two numbers. We did it with two numbers itself. We don't. Yes, understood. Good question. Yeah, this was a good question. So the time complexity in best case, like if you applied the dynamic programming vector, it would increase your space complexity. Right. This is the best possible approach with variables itself. So here the time complexity would be big of n, and the space complexity would be big of n. Obviously, we can. Right. I hope these states are also fine. Right. Everywhere the if they both match, then we will increment both the elements and all that.
अंशु कैसे होगा ये सब कुछ? Sorry. God. Feels like something is not good. Okay, let me go to office, bro. I have to take shower. I need to cook something. Bye bye, take care, and I'll see you later. Okay, yeah. And if you wanted, you can see my two NDVS are hanging. Bye bye. I got the intuition, but I feel like how to grasp it, how to get it like when you are solving. Definitely practice will it will come with practice.